Hi everyone, in this video we are going to discuss limiting reagent, which is also called limiting reactant. So I will use the two interchangeably. Just know that whenever I say either of these, I'm talking about a stoichiometric problem. So the best way for me personally to describe limiting reagent is to actually talk about baking. So let's just say we're going to make some cookies in the most simplistic, most boring recipe ever. So let's just say for our example, we need 1 cup of flour. And let's just say we need a half a cup of sugar. And then the most important ingredient, obviously, we need a 1/4 cup of chocolate chips. We want to make good cookies. Okay, so we're going to mix these all together, plus some love and some vanilla and baking soda and whatnot. Mix that all together and we get some cookies. So if we wanted to make this very, very simple, we would say here are our reactants and we're going to make our products, which are cookies. So let's say now it's at the end of the week, it's Friday night, we've had a horrible week, and all we need to keep ourselves from crying is to make some cookies. So you go to your pantry and you see that you actually have 1 cup of everything. Okay, so you have a cup of flour, you have a cup of sugar, and you have a cup of chocolate chips. Can you make cookies? Well, let's go through it. We need a cup of flour, we have a cup of flour. Perfect, not an issue. We need a half a cup of sugar, but we have a cup of sugar. So we actually have a half a cup of sugar extra. Perfect, not a big deal. Now we're saying we have a cup of chocolate chips. We only need a 1/4 cup of chocolate chips, so we have 3/4 of a cup of chocolate chips extra. So this is perfect. We could absolutely make some cookies, no big deal. We'd have a fantastic Friday night. All right, so now the following week, having an even worse week, having a terrible week, we need to make more cookies, okay? This time though, since we've made some random version of cookies, we only have a half of cup of everything. Okay, so now this time we see, okay, we need a half of cup of sugar. We have a half of cup of sugar. Perfect, not an issue. We need a 1/4 cup of chocolate chips. We have a half a cup of chocolate chips. So we actually have a 1/4 cup extra of chocolate chips. But now here's the problem. We need a cup of flour, but we only have a half of cup of flour. So in this example, we would say that we cannot make cookies. So this would be no cookies. Very, very sad. And the problem is because we are short a half of cup of flour. So for this example, we would say that flour is actually our limiting reactant. And so what we are basically saying is we don't have enough flour to properly make that cookies in that recipe that we wanted to use. If we wanted to cut everything by half and say, okay, let's use a half a cup of flour, a 1/4 cup of sugar, and then an 1/8 a cup of chocolate chips, we could still make cookies. But just with that given recipe, we can't do it. We don't have enough flour. So what we need to do is take this concept and translate it into chemistry. It's the exact same thing. So don't let go of cooking and baking. It's the exact same concept, but we're just going to use chemicals now instead of flour and cookies, and we're going to use moles or grams instead of cups. Easy, right? All right, so the best way to do this again is talk through with an example. So let's focus on the combustion of pentane. So C5H12 plus 8O2 going to 5CO2 plus 6H2O. Here's our balanced chemical equation of the combustion of pentane. All right, so now let's say we are going to start off with 0.85 grams of pentane and 0.35 grams of oxygen. That's just what you have in your pantry. That's how much you have. Now what you want to do is figure out how many grams of water you can actually produce with these reagents. So the best way to do that is simply to take this number and convert it to grams of water, this number, convert it to grams of water, and say which is my smallest number. Because your limiting reagent is going to tell you how much you could possibly make with the smallest amount possible, okay? Again, best way to do this is through an example. It seems confusing, we'll work through it. First thing I need you to do is do a simple calculation for me. How many grams of water can be produced from 0.35 grams of oxygen? Go. All right, did you get an answer? Hopefully you did. If you didn't, that's okay. We're going to work through it together. So let's start off with something very, very simple. We need to start off with what we know. So we know that for this specific problem, we have 0.35 grams of oxygen. We're in grams of oxygen. We need to convert to moles. So the molar mass of oxygen, diatomic oxygen, is 32 grams per 1 mole. we know using our mole-to-mole ratio from above here that we have 8 moles of oxygen to 6 moles of water. Remember, we're trying to get to water, so that's the goal. So 8 moles of oxygen to every 6 moles of water. Now, we're not asking you for moles of water, we're asking you for mass of water, or grams of water. So we need to take this one step further. So for every 1 mole of water, we have about 18 grams. That's our molar mass of water. So now if we calculate this properly, we should see that we actually end up with something like 0.147 grams of H2O. Now, if you recall from the previous video, we actually already did the other math component. So let's put this all together in a little summary. So when we have 0.85 grams of our pentane, so our C5H12, we can actually create 1.27 grams of H2O. However, when we have 0.35 grams of oxygen, these are our two starting materials, remember, we can only create 0.147 grams of water. So essentially what we just figured out is that it's great, it's absolutely wonderful that we can create over a gram of water with the amount of pentane that we have, but with the amount of oxygen we have, we can only create 0.147 grams of water. That's it, 0.147. We do not have enough oxygen to make 1.27 grams. We can only make 0.147 grams of water. So what this means is that oxygen is our limiting reagent. Now I use LR and I circle it. I was taught this my sophomore year of high school and I stick with it. It's something that just stuck with me, so I stick with it. So identify your limiting reagent right away. So because we only have 0.35 grams of oxygen, we can only create 0.147 grams of water. We cannot create 1.27 grams of water. This means that oxygen is our limiting reagent. All right, so now, why don't you guys do a problem here and see if you can identify every single piece, okay? This is going to be kind of complicated, but do the best you can. How many moles of carbon dioxide are produced from the combustion, we're obsessed with combustion in this unit, from the combustion of 3 grams of hexane and 3 grams of oxygen. So I want to know how many moles of carbon dioxide in theory can be produced from 3 grams of hexane and 3 grams of oxygen. So in lab, I take 3 grams of hexane, 3 grams of oxygen, I react it together. How many moles of carbon dioxide are produced? Go. All right, did you get an answer? Hopefully you did. If you didn't, don't worry about it. This is definitely by far the hardest problem we've done this entire semester. So just hang in there, we'll get it together. All right, first thing you have to do is you must derive a chemical equation. If you don't do that, you have no shot at even getting the correct answer here. All right, so we said combustion of hexane. 2 big clues. Combustion, our hydrocarbon is hexane, so C6H14 times 2 plus 2. Then we go plus oxygen. Then we create carbon dioxide and water in any complete combustion reaction. Now we have to balance it. We have 6 carbons on the left side, so we need to put 6 on the right side. We have 14 hydrogens on the left side, so we need 14 on the right side, so 7 times 2. Now we have to check our oxygens. We have 7 plus 6 times 2 is 12. That gives me 19 oxygens on my right side, and I have 2 on the other side, so we just have to do 19 times 2. Remember, I hate that. I hate the fractions. You absolutely need to get rid of that for me. So you multiply everything by 2. So this becomes 2C6H14 plus 19 oxygens going to 12 carbon dioxides plus 14 waters. Okay, a lot of math here. We have to check this and make sure this is right. So we have 2 times 6, 12 carbons on the left side, 12 carbons on the right side. That's good. Then we have 2 times 14, 28 hydrogens on the left side, 2 times 14, 28 hydrogens on the right side. Beautiful. Okay, now we need to look at oxygens. So we have 12 times 2 on the right side, so that gives me 24, plus 14 again on the right side, so 24 plus 14 gives me 38. Then we can come over to the left side, 19 times 2 also gives me 38. Whew, okay, good. So our reaction is definitely balanced, and so we have a beautiful, beautiful chemical equation right here, okay? So now we can move on to step 2. So the goal is to determine how many moles of carbon dioxide we can create from 3 grams of hexanes and 3 grams of oxygen. So essentially what we need to do is 2 very different but separate stoichiometry problems to try to convert 3 grams to moles of carbon dioxide. So let's just start off with our hexanes. So we have 3 grams of C6H14. Now we're in grams, so we need to put grams at the bottom, and we have to go to moles. So for our grams of C6H14, we have 1 mole of C6H14. This would be our molar mass. So for hexanes, we know that we have about 86.18 grams of hexanes per every 1 mole. All right, so there's that. Now we're in moles of hexanes. We have to go from hexanes to moles of carbon dioxide. So moles, moles of hexanes is going to be on the bottom. And then moles of carbon dioxide is going to be on the top. So we go up to our chemical equation here. We see that there are 2 moles of hexanes on the bottom, 12 moles of carbon dioxide on the top. That's all we're doing. We're just trying to figure out how many moles of carbon dioxide we have. So we check our units. Grams of hexane, mole of hexane, left in moles of carbon dioxide. Beautiful. If we calculate this out, we have something like 0.208 moles of CO2. All right, so now we can do the exact same process, but for oxygen. So we know we start off with 3 grams of oxygen, and right now we're just trying to determine how many moles of carbon dioxide 3 grams of oxygen could theoretically produce. So we need to use our molar mass of oxygen. We know we have about 32 grams of oxygen per every 1 mole of diatomic oxygen. We look at our chemical equation, and we can see we have 19 moles of oxygen per every 12 moles of carbon dioxide. So we use that mole to mole ratio again. Now, if we solve this out properly, we get an answer of 0.059 moles of carbon dioxide. So what we can do right now is come down here and put a little summary. So we can see that 3 grams of hexane, so our C6H14, creates 0.208 moles of carbon dioxide, whereas 3 grams of oxygen can actually create 0.059 moles of carbon dioxide. So my question to you, which is the limiting reagent? So you have 4 options here. It can either be hexanes, oxygen, water, or carbon dioxide. Which one is it? All right, did you get an answer? Hopefully you did, and hopefully you listened to what I just said and said, all right, she's tricking us, they're teasing us. There are only 2 options here. We are talking about a limiting reagent, so that is something that has to be on the left side of your chemical equation. It is a reagent. Our only options here are C6H14 or O2. It cannot be carbon dioxide and it cannot be water because those are products. Those are on the right side of the equation, cannot be an option. All right, so all we have to do now is see which one of these can give us the fewest moles of the product. So we go back up here. 3 grams of hexane gives us 0.2 moles of carbon dioxide. 3 grams of oxygen gives us 0.059 moles of carbon dioxide. Our limiting reagent is 100% oxygen. So what I do in theory, every time I do this, I put a little X over this number so that there's no way I get confused. I come over here, I write a little LR, I circle it, and then we're done with the problem. Good luck, take care of yourselves, drink water.